Welcome Colloquium. This is a special Colloquium, the fifth lecture in our notable alumni lecture series. The previous four notable alumni speakers all had a distinguished career in top research universities. However, we pride ourselves in CAM on the fact that there isn't just one way to be successful in applied mathematics coming from this program. And that whatever is your definition of success, we will help you along to get there. And our speaker today is a living proof of really diverse paths to success and definitions of applied math careers coming from here. So Scott Clark is an entrepreneur, and fantastically for us, his company grew out of things he did at Cornell. We're very excited about it. He's also an employer. I hope those of you about to graduate already talked to him. And he employs CAM students, plural. So we're very excited to have you here today. Before I yield the stage to his advisor, who will do a more personal introduction, some swag, which we usually do for all the CAM speakers. So there is a CAM jacket, CAM travel mug, so in case you need a drink. Yes, oh, you have one, yes. And also some big red cheese, Cornell cheese.
It's been years, I can't wait.
Yes. So, thank you for coming, and we're very excited to have you here today.
So I want to take a moment to just express gratitude to Scott. So Scott actually was my very first PhD student. And you know, getting a PhD is really a growth experience. You learn how to become a researcher, how to think, you know, independently and deeply. But for me, advising Scott was very much a growth experience, and there's so many mistakes that I made. I'm very appreciative that he turned out fine. I'm actually quite successful in spite of all of the mistakes that I made. Something that's very special about Scott is that obviously he's very entrepreneurial, and something that he taught me from early on is the importance not just of thinking about, you know, extending the body of what we know, but also the importance of building something that people are going to use. One of the things that he did in his dissertation was to develop a piece of software for evaluating the quality of assemblies for high-throughput sequencing in metagenomics. And not only did he develop this method, but also he developed a set of software tools where people can really use this method, and actually still continue to use this method. And it's one of my most widely cited papers, and also one of Scott's most widely cited papers. So that's something that I'm very grateful for. Another thing that I'm very grateful for is the work that he and his company has done for Bayesian Optimization, the field that I work in. They do a great job of advocating for the field, advertising what the field is, hiring people who work in the field, supporting research, supporting workshops. And then the last thing I'm grateful for is that he serves as an example of how we can be entrepreneurial, how we can use, you know, applied math in order to actually build things that have an impact in the world. And it's something that I hope some of you can go on and do in your careers. So let's thank Scott.
Thank you, Peter and Alex, for the great introduction. Really honored to be here. I remember when I was sitting on that table in the back watching some of these colloquia when I was a student. And it's really honoring to be here on the other side of it. So thank you all for inviting me. And hopefully you all get something out of this talk. I wrote it last night on the campus-to-campus bus from New York. This is the first time I'm giving it. But I tried to design it so that there's a little bit for everybody. So hopefully, no matter what your field is, what you want to do when you grow up, there's something here you can take away from it. So that was my goal. Happy to dive deeper on any of this in the whiteboard over coffee afterwards as well too. Throughout the talk, I like to keep it somewhat conversational, so if people have high-level questions, I'm happy to address them here to make sure that we all have understanding, especially since it's the first time I've given this particular version of this talk. And if there's something super deep, we can just take it offline afterwards. So please raise your hand throughout if there's anything you want to talk about. Cool. Again, this is a bit of a piecemeal. I'm going to be talking about how I came to understand and love this problem in space that I eventually started SigOpt around. I'm going to talk a little bit about Bayesian optimization from a very general perspective, trying to build up some intuition about how it can help attack this problem that I kept running into. I'm going to talk a little bit about what it meant to take that plunge from publishing open source, working on this field kind of from a more academic perspective, into actually starting a company around it, one that now employs 30 people, including a handful of campsters, and services businesses, universities, and governments around the world. And then I'm going to dive a little bit deeper into some real world kind of applications and some ways that we've had to modify kind of the vanilla Bayesian optimization approaches that we originally started with, based off of what we saw in the real world versus maybe what we were building towards academically before. So a little bit of everything. So we'll start with how I came to run into this problem. This might be familiar to a lot of you. Showed up at Cornell after doing some math and physics at Oregon State. Did some work in Germany as well on some quantum physics work, but it was basically a big hodgepodge of stuff. And I graduated from Oregon State, and I was like, I have no idea what I want to do. Who hires physicists with just an undergraduate degree? A safe place to kind of figure that out would be grad school. Luckily, too, this was 2008, and the financial crisis was in the process of happening, so it ended up being an extremely safe place to kind of wait out the storm. But I found my home here at CAM, and this was a really unique place where I could work with a bunch of different people from a bunch of different fields. I was able to find Peter in the operations research department, work with Steve in the math department, collaborate with a bunch of different people, and I think that's a really unique opportunity that you all have here today, and a super lucrative one that you should take advantage of. So being able to speak interdisciplinary, being able to find these cracks and crevices between well-studied fields is an extremely valuable thing. So I highly encourage any of the students in the room to continue to try to find interdisciplinary research, take classes outside of your field, really try to see the areas that are less examined, because sometimes there's some really fun stuff there, and sometimes you can find some really useful low-hanging fruit. So my career at Cornell was a bunch of jumping around to different national labs, some places in industry. You can see this terribly rendered photo here on this projector of me that looks almost satanic, but this is me in front of a government supercomputer. It was one of the fastest computers in the world at the time. This was Hopper at the NERSC supercomputing facility in Oakland. A lot of my research focused around how I could take hard, real-world applied problems and then manipulate them into computational code. So I had a DOE CSGF fellowship, so I was highly encouraged to do that, but this was something, again, that I had a large passion for, and it's that goal of being the interdisciplinary person in a group, which, again, campsters are uniquely qualified to do. If you can know the most about something, even without being an expert, then you can provide a lot of value to a bunch of biologists, for example, by being the one that knows how to do Python, or a bunch of physicists if you're the one that knows how to do optimization. And that can be a very unique way to make a big impact instead of, again, just focusing on your core domain.
You should maybe say something like that. It was in the summer.
Yeah.
How did you do all this?
Oh yeah, sorry. So over the course of different summers, I would go to different national labs. Again, part of that fellowship, but they actually accept students without DOE fellowships as well. At Los Alamos, I studied some different gene alignment work, so some bioinformatics work that I then extended when I was at LBNL / the Joint Genome Institute, doing that paper that Peter talked about, something that I don't touch at all today and was a summer project, but now has well over 100 citations, I think. And then spent some time at Bloomberg as well. This was my slow foray out of academia. As Alex said before, there's different career paths for Camsters. The national labs felt like a kind of safe middle ground between academia and industry, where I could have a little bit of my cake and eat it too. But I really found my passion for the fast-paced world of more pure industry after working at Bloomberg in Manhattan for a summer. That concept of just constantly iterating, shipping fast, failing fast, learning as quickly as you can, and then just trying to see if you can make some value out of that was something that really spoke to me. So if academia doesn't speak to you, there's many different opportunities for you to leverage what it is you're learning today. And I highly, again, recommend not only doing interdisciplinary research, but trying to just get outside of Ithaca and seeing what the rest of the world looks like. Quick plug, we're hiring grad students. We do PhD internships too, but so does everybody else these days. I think people have figured out that people like yourselves are incredibly valuable to companies. So I started to see a similar pattern throughout all of these different summer internships at different national labs, different universities, different things that I was doing. I saw the same problem come up, and one definition of insanity is doing the same thing over and over again and expecting different results, but that was effectively what I was doing. I would build some great system with the help of collaborators that had a lot of domain expertise and context awareness and genome assembly algorithms or computational fluid dynamics or quantum physics or something like that. And a lot of the fun stuff would get done. And then at the end, we had to fine-tune whatever we built in order to get to the best possible version of it. So we could get a better paper, beat some baseline, whatever it may be. But again, this was completely orthogonal from that domain expertise and context awareness that might have actually built that underlying system. And it's like just dropping you in the cockpit of this F-15 and saying, here's a bunch of knobs and levers, figure out the right setting, and go fly it. And oh, but by the way, sometimes it might be snowing, sometimes it might not actually be an F-15, it might actually be a stealth bomber, maybe it's a submarine sometimes. Each one of these problems needed to be attacked kind of fundamentally, again, from the ground floor. And this was something that, as the low man in the totem pole, fell upon me to go, okay, figure out kind of this nuisance part of the problem, get to the right settings. We're going to start working on the next cool thing that actually advances the field. And really, what we needed to do was come up with some way to have this process be able to be tuned better. So you can think of this as black box optimization, or kind of sequential optimization. We want to learn from how previous inputs affect the outputs to make more intelligent inputs, so that we can get to the best version of this system much more efficiently than trying to brute force it or something like that. But not only do we need to do this for individual projects, wouldn't it be great if we could do this for general purpose projects? Because again, I had this problem in every single paper I tried to publish at Cornell, but I would walk around the department and ask people in financial engineering, in biological systems, and all sorts of different things, and they'd have the same thing. They'd be like, yeah, I built it out, and now I'm just waiting for the cluster to return because I'm just trying to find how to configure it or whatever it may be. So a general purpose system for this could be extremely valuable to help people accelerate the research, augment the workflows that they're already doing today in this very orthogonal fashion. And that's when I met Peter, took his class Optimal Learning, and realized that there was a field behind this that could actually help try to attack this problem where you have f of x, and you want to find argmax of f of x. Maximize x within some domain as efficiently as you possibly can. Yes. So people call this many different things. Black box optimization is a very common term for it. Model tuning, optimal learning, adaptive design experiments, hyperparameter search, sequential optimization. This has been independently invented a couple of times in a couple of different fields. There's been a big push in it over the last few decades as some of these systems have gotten much more complex. There's been a lot of different research that has gone into solving this though. Black box optimization is a problem that's existed since people started doing experimentation. I have some system that I can't necessarily analytically define. How do I configure that system to get what I want out of it? Everything from tuning your car, to finding the optimal ingredients for beer, to setting your hyperparameters when you're doing a deep learning optimization. All of these things kind of face the same problem. So there's many different ways to attack this. And I'll walk through a couple of them here. But again, global optimization and black box optimization has many different paths. I'm going to be focusing mostly on Bayesian optimization, but I'll talk about the ways that we see, sorry.
This question, you said hyperparameters in learning, but not the parameters themselves?
Correct. So the distinction here is hyperparameters are the parameters that you need to set ahead of time. They're not learned by the system. So these are the things that you would manually have to set in a configuration or whatever it may be. Think the architecture or the learning rate of a deep neural network, not the individual weights that are learned via stochastic gradient descent or something like that. So these are the problems that are inherently trial and error, inherently manually set today. And most systems, all machine learning systems, but most systems do have these free parameters that are not automatically.
Why is they conceptually different from the other? I mean, it's optimization. That's also optimization. So what's it like?
Correct. So the difference between black box optimization and potentially other forms of optimization is you may have more information here. You may have derivatives, gradients, Hessians. You may be able to make some strong assumptions about convexity. There may be an analytic way to actually write down this function. Black box optimization assumes you only have inputs and you have outputs, and that's it. So different branches of optimization, even within those, there's different sub-branches and things like this. But what we're focused on attacking is something where you as an expert need to configure the system and see what the output is. And then potentially reconfigure the system and see what the output is. Not something where you can write an intelligent method for learning that necessarily. Make sense? Thank you for the clarifying question. Cool. So we've been talking to a lot of different people in industry about this problem for the better half of the last decade. We see a bunch of different ways that people try to attack this problem in general. And one thing that's fundamentally different about industry and about startups in particular than academia is your goal is not to solve the problem perfectly. Your goal is not to prove that you have a better solution than someone else. Your goal is to say, what are you doing today, and can I do better? And so the bar is slightly different, where it's not 100% solution, but it's just some delta over whatever solution they have today. So I'm going to walk through some of the different techniques that people apply today and talk about the different pros and cons of them. But 90% of the time when we talk to people in industry, or 95% of the time, they're using one of these methods. So one of the #1 most used methods for doing black box optimization is manual search. So just as a human, try a bunch of different things, try to get some intuition, and then hopefully that intuition pays off, and maybe you'll start to configure the system. This can work okay in 1 or 2 dimensions. In higher dimensional spaces, humans get pretty bad at doing optimization in their head. No one can really visualize a 10-dimensional space, and even if they can, they're doing local optimization more often than not. This is the kind of grad student descent that a lot of people talk about. Just go figure it out and then come back with a better result. This is pretty pervasive in industry, but again, orthogonal to that domain expertise, expert intensive, and inherently trial and error, something that humans aren't good at. So for more complex systems, people like to move to more automated methods, things like grid search. This is an exhaustive search of the space. Imagine trying to climb a mountain by laying down a bunch of lat long points and just going to every single intersection and recording the altitude, and then after you've done your entire grid, you see which one had the highest altitude. So hopefully there's a couple things that seem wrong about this. One, that exhaustive search scales exponentially as the dimensionality of the problem increases. Two, is you're almost surely going to alias over the actual optima anyway. If it's a continuous space, you're not actually going to hit everything. You're going to have to discretize it in some way. So it becomes intractable, it becomes somewhat inefficient, and at the end of the day, does not scale to a lot of the real world problems that we see. So these are extremely common, and a lot of open source libraries and talks tell you to do things like this. There was a paper a few years ago that talks about, well, instead of doing grid search, you should do randomized search. And the intuition here is if you can make some somewhat loose assumptions about the response surface you care about that mountain, then random search in expectation actually is extremely efficient in finding something within some threshold of that actual peak. But this is like trying to climb that mountain by getting in an airplane, putting on a blindfold, jumping out, and just hoping you land at the peak. And then just getting back in the airplane and doing it again and again and again and again. Again, your math spidey senses should be tingling. This doesn't seem like the best way to solve this problem. So one thing that grid search and random search have in common is they don't learn anything. They take that precious information that you've gained by jumping out of an airplane or maybe running a physics simulation for a 24-hour period on a supercomputer, and they just take that information and they're like, okay, I got the value, and I'm just going to throw that away for now, and at the very end, I'll just sort the list. So again, maybe there's something we can do between there. So there's been a lot of research in global optimization over the last few decades, as I talked about. A lot of it relies on intuition from other fields of science. So evolutionary algorithms draw a lot of inspiration from biology. The idea here is we're going to go on that mountain and we're going to plant trees that do slightly better at higher altitude and just let them slowly disperse their seeds over many generations, and eventually we'll probably have a tree that's at some sub-peak, if not the peak. So that can work okay in the sense that you can kind of slowly evolve to this best solution, but it requires a large number of underlying evaluations. You need to try many different populations, let those populations evolve, and if it's very time-consuming and expensive to evaluate that underlying process, this can, again, become intractable or at least inefficient. There's other methods, particle-based methods, things like simulated annealing, things that draw more from kind of physics intuition, which I won't go into here. But the concept is, again, lots of sample evaluations, lots of attempts at climbing that mountain without actually necessarily getting there in any sort of efficient way. And then in comes Bayesian optimization. And the analogy here with the mountain is, as you're trying different things, you're building a map. You're building some representation for what you think the rest of that mountain range looks like, and you're leveraging what you know and what you're uncertain about in order to decide what's the best next thing to try. And so this ends up being an extremely efficient, derivative-free optimization method where you're doing a lot of work on that map instead of a lot of work trying different things on the mountain range. And so again, for a lot of our customers, where it may take an hour, it might take a day. One of our customers is the largest streaming service in the world. You're probably all subscribed to. When they tune the recommendation engine, it takes days on thousands of GPUs in order to actually train it. And so in order to do that efficiently, you need to make sure that you are leveraging every piece of information you possibly can and only sampling that as infrequently as you possibly can. There are some pitfalls to this, which I'll go into throughout the rest of the talk. It can be tough to parallelize. Bayesian optimization can be complex. There's a lot of pitfalls and gotchas. It doesn't always work out of the box. Sometimes it requires collaborating with someone to build a very specific application to it. But largely, these have been things that, at least historically, have stymied people when trying to apply this method versus these maybe more trivially codable examples like random search. You can grab a random vector from your domain, then you've coded random search.
Question.
Yes.
So in the cons, you have not scalable, inefficient, very resource intensive. So these kind of all sound like the same thing.
That's fair.
Okay.
Yeah, so in a lot of it, it is the fact, the inefficiencies. The inefficiency does kind of go down throughout this. So grid search is worse than random search, is worse than some of these more intelligent methods if they're at least configured a little bit. But at the end of the day, most of the reason why customers pay for SigOpt is because they want to save wall clock time, or they want to save compute time, or they want to save expert time. And all of those things come back to money, whether it's opportunity cost or whether it's hard costs. But yeah, time is the main thing that we're trying to do here, and that's where this kind of efficient global optimization techniques, the efficiency is really what we're striving for. But thank you, I'll clean that up to make it a little bit more clear.
And I lost the analogy once you get to Bayesian optimization with the mountain. How does
Okay.
that map on the
Yeah, so you're in a mountain, and you're trying different locations on that mountain, and every time you try a location, you're going to build a new map for what you think, like a topographical map of where you think the peak actually is, where you're uncertain about kind of the altitude of things, and you're going to use that map to decide what to try next. And when you try that, you update your map, and you get a better representation of what the mountain actually looks like. And go
This
on.
isn't a kind of like, you're not necessarily doing local thing like you do one
Correct.
station, you look locally, determine something about.
Yeah, so it's not like a hill climbing or more convex method where you're just kind of looking in each direction and then just stepping upwards. Again, that can be extremely expensive in high dimensions, even just sampling a very simple stencil around where you're at. And it is a local method as well. It makes some pretty hard assumptions, again, yeah, about the locality of the optimum and potentially continuity or differentiability of it as well. Which may or may not be true in the mountain's case, if there's cliffs. Stretching this analogy now, but I'm happy to take it all the way to the ground if you guys want. Cool, so Bayesian optimization seems pretty good, right? How does it actually work? So again, we have this system on the left, and we can sample different configurations and observe outputs. And we want to leverage that output information to decide what's the most intelligent thing to sample next, and repeat. So again, we try different places on the mountain, we learn how well they are, what their altitude is, we build a map, we use that map to decide where to go next, and repeat. What this looks like a little bit more mathematically is what's often called in the research literature sequential model-based optimization. So it's model-based in the sense that we're building a surrogate model, or that map, of what we think the real world looks like. So we can represent the information that we have so far to say, what do I think will happen in places where I haven't sampled yet? So what we have here is a representation of a Gaussian process and 5 points being sampled in this one-dimensional space. So let's say I'm trying to maximize this y, and I have x here. I've sampled 5 points. Each one has a specific y value, maybe with some potential uncertainty or noise. If I'm optimizing a stochastic process like an algorithmic trading strategy, where a neural network is being randomly initialized or something like that. So what we want to do is we want to build up this representation for what we think will happen when we sample elsewhere. So this might sound like a polynomial spline or a regression or something like that. One way that it differs, though, is we also want to represent how uncertain we are about that assumption. So a Gaussian process here can be thought about in a couple different ways, but it's basically a representation in this graphic of all of the different potential paths this underlying function could have. We can draw different functions from the Gaussian process to say, this is one potential underlying function that we're trying to optimize. The mean of the Gaussian process might be the most likely underlying function that could represent it. It goes through all the data points. It looks pretty good. It has some smoothness parameters that I'll talk about in a second. So that's kind of the functional way to think about Gaussian processes. Another way to think about it is, at any given point I want to try, I might be able to represent that with some Gaussian distribution. There's some mean expected response, and then there's some uncertainty associated with it as well. Okay, so now we have this kind of stochastic surrogate model that represents what we know and what we don't know about that underlying space. So one thing we could do now is just try to optimize the surrogate function to say, what's the best point that this thing's going to happen, and we go from there. But what we actually want to do is say, what's the point that gets us potentially the most information, or has the best probability of improving the best thing we've seen, or the best expected return on the best thing we've seen so far? Our goal is to do global optimization here, not necessarily resolve local optima in this surrogate model. So what we do is we apply what's called an acquisition function to it. In this case, expected improvement. How much do we think we're going to beat the best thing we've seen so far by in expectation? So what we're looking for here is parts of the space that have kind of a reasonable mean, but also have enough uncertainty that we're willing to make a bet on it. Maybe you only have a 1% chance of actually beating the current best, but if I do beat it, maybe it could be really good. So I'm willing to place my bet there and decide, okay, let's sample that point. And we do it, get a piece of information back. Turns out that was a pretty bad point, but that allows us to update our map, update this surrogate method. We're learning as we go and building a better and better representation of that underlying space, getting more fine-grained detail, and then leveraging that to decide what to sample next.
But it seems like at the end of the process is you're back to the original problem.
Potentially. So I'll get to that in a second. Excellent point. What about all the tunable parameters and Gaussian processes? Is that what you're hinting at?
You know, it just feels like, what if you get a perfect model, then you're back, and you have to optimize that, which is where you were at the beginning.
Yeah, okay. Great question. So one nice thing about Gaussian processes and these specific acquisition functions is we might have nice analytical properties associated with them. So instead of treating this like a black box function, we might be able to throw the kitchen sink of other optimization methods at it in order to make sure it's not turtles all the way down, but we just solve what this is. Turns out there's still a lot of tunable parameters within Gaussian processes and other Bayesian optimization methods, and that's largely why SigOpt exists, so that we can auto-tune those for our customers. I'll get to that in a second, but this was part of the motivation for starting the company. Yeah.
So if you gave me a Gaussian process, is the acquisition function a thing that people know how to calculate?
Yes,
That's
so
like standard, right?
given a Gaussian process, you can calculate an acquisition
Okay,
function.
so that's not, so, all right, so
Yeah.
that's just sort of like, that's available, and so then the product.
Correct. It might be numerically difficult to calculate that, but
Yes.
there are ways to do it.
Okay.
Yeah. But again, one thing worth pointing out here, though, is we've shifted the problem. So in this example here, I've only sampled that underlying function once. But I can do a bunch of work here to decide what to do next. So instead of relying on slowly hill climbing or evolving that or my suggestions on that specific space, I've mapped it into this surrogate space where maybe things are a lot cheaper, maybe I can parallelize things better. Like I don't need to care as much because it's a fractional cost. So when I do go over here, I know exactly what I'm doing. Yeah.
So in the game that you're playing where you build your model and then you decide where's your best bet for tuning your model, like what point should you sample next? My intuition might be to pick the point with the most uncertainty because I have the best payoff. But it looks like, at least in this toy example, the most uncertainty is kind of right in the middle, but you've picked a point that's to the left. Is there...
We're potentially on the edges here.
Right. Is there a reason why you might not want to pick the point with the most uncertainty to sample next?
Yeah, because again, our goal is to do global optimization at the end of the day. So we want to find the point that gets you the best result after some finite number of steps through this process. And you could have a lot of uncertainty somewhere, but it could still be extremely low probability or expected return by sampling that because you know that it's bad. You don't know quite how bad it is, but to a certain extent you don't care. Because, and this is where it differs from like a standard method where we're just trying to get a good regression of the underlying space. We only care about that insofar as it leads us to a better global optimum. So bad, we can ignore. Good, we might want to resolve. Things in between, we might want to explore to see whether or not they're good or bad. But this allows us to kind of zoom in on local optima, but ignore parts of the space that, like something like a grid search, would just plod through. It's bad, still bad, still bad, still bad, still bad. Yeah. Good question. Awesome. So, kind of hinted at some of these questions. So Gaussian processes themselves, how are those defined? Have you actually solved this problem for me or just shifted it? So Gaussian processes are largely defined by what's called the covariance kernel. So how much does sampling a point A give me information about a point B? How similar are they? Can I actually use information from climbing one part of the mountain to tell me anything intelligent about another part of the mountain? Does that decay very quickly? Like, is it only very local information? Does it give me longer range information, etc.? And it turns out different covariance kernels, especially as you start to look at more heterogeneous parameter spaces of integers, categories, and continuous functions, can have a vast effect on what surrogate models you actually build. So what I'm showing here is 4 different Gaussian processes with the exact same input data and just slightly different length scales on one specific type of kernel. And what we can see is we might be able to underfit the system, just have this kind of line that kind of cuts through everything. We might overfit it where there's a bunch of uncertainty the second you step away from a known point. We might be able to find things that look somewhat reasonable. Turns out there's different ways that we can kind of quantify this reasonableness, and that allows us to fit the best Gaussian process given the information we've seen so far. But this is definitely something that you need to have some good prior knowledge on, potentially by solving similar problems, or update as you go. And again, there's different acquisition functions you could use. So you defined one that is a legitimate acquisition function in the sense of maximize uncertainty. There's other more classic ones from the literature of what's the point that has the best probability of improvement. This is a somewhat conservative approach because maybe I'm only taking points that's 99% chance that I'm going to succeed, but I'm going to get a very low return from it. I don't necessarily care about the return, I just want to make sure that I'm minimizing this regret of like, oh, I want to make sure I never do worse or have a low probability of doing worse. Expected improvement, again, takes a factor of that, but it also quantifies, well, if you have a 1% chance of getting 100 gain, that might be better than a 99% chance at a 0.0001% gain. And it ends up being a little bit better in certain circumstances of doing this trade-off between exploring uncertainty and exploiting local information. But there's a bunch of other methods. Peter has worked a lot on knowledge gradient methods. There's upper confidence bound methods. You can define arbitrary acquisition functions like most uncertainty or highest mean or something like that. And each one have these different trade-offs. And what you can see here is of 4 different acquisition functions, they will lead you down different paths. So different surrogate methods will build different maps, which will lead to different acquisition functions that could also lead you in a different direction, which then cause you to update your map differently. And it's important to note that some of these decisions and choices will lead to fundamentally different types of search and efficacy of search. So the SigOpt team has done quite a bit of research in this. There's some seminal textbooks and papers out there that I highly recommend reading if you want to dive deeper. Gaussian Processes for Machine Learning by Rasmussen and Williams, free online from MIT Press. Efficient Global Optimization was a paper 2001, I think, or something like that. 98, that's right. Yeah. And that's a great kind of survey and intro to this field. We've done a lot of work in this as well, writing a little bit higher level kind of technical blog posts. Still about 50% law tech, but it provides some examples and some GIFs and things like that to kind of get some intuition behind it. Highly recommend checking some of these things out. And all of those kind of seminal papers and books are cited in these blog posts as well if you want to dive deeper into kind of how does this actually work at a high level. Cool. So the third of 4 sections here is about, okay, now that I've run into this problem a bunch of times, what am I going to do? Well, I decided to leave academia and join Yelp. I joined the ad targeting team at Yelp. It was relatively small at the time, still a kind of growing startup pre-IPO. But what I didn't realize when I joined Yelp was I hadn't run away from my problem successfully. I had just shifted the problem a little bit. So instead of tuning different models or systems that I had built with collaborators at national labs and things like that, now I was faced with an advertising system that had been built over the course of the last decade that itself had lots of tunable knobs and levers in it. How far away do you show ads? Different hyperparameters for machine learning models for deciding which ads to show, recommendation systems, and things like that. One major difference was, instead of getting that answer right, meaning better papers, if you could get that answer right at Yelp, a whole bunch of money came out the other end. So it became a very lucrative problem to solve, and I ended up extending some of my PhD work to write the open source library Mo with Peter and another one of Peter's students, as well as a handful of people at Yelp. And what I realized was very quickly, it got over 1,000 stars on GitHub, and I was invited to give talks. I gave like 30 talks around the Bay Area to all the companies, Netflix, Google, Amazon, Microsoft, LinkedIn, etc. And they all said, we have the same problem too. We're not building an advertising system. Maybe we're building a recommendation system. We're building people you may know at LinkedIn. We may be building all sorts of different things. But they were like, we have this problem too. The problem was I had taken their optimization problem, and with the open source of Mo, I had given them an optimizer problem. All of those gotchas, all of those decisions you need to make about Gaussian processes, about kernels, about which methods, things like that, even whether or not you're going to use a Gaussian process or something else, all of those were kind of left to the user, which makes sense if you're a grad student publishing things for grad students to use, but doesn't make sense if someone just wants to get the right answer. So that's when I decided to quit Yelp and start SigOpt. So here you have me on the left in kind of hallway / closet in my house. This was a picture from one of the original TechCrunch articles about when we launched SigOpt and closed our first round of funding. You'll notice some fun things here, like we didn't realize that we should clean up the office at all, so a bit of garbage over here. Some early coding. This was back when I actually still got to code instead of being successful enough to get myself out of the part of the job that I love the most, and now I do mostly sales. But it's been a really great experience to be able to take this problem and this idea and now grow a team around it, grow a business around it. Here is a snapshot of some of the team. I don't think Eric is in this one, but this is Mike McCourt, who was a CAM graduate student while I was here and joined SigOpt in the early days. He's a PhD intern that we had, and we kind of cycled through one or two every term. But it's been a really great experience to kind of grow that from where it once was. And really, our goal is to help accelerate and amplify the impact of modelers. People have domain expertise, they have context awareness, they have something that they can uniquely do, and we want to help provide tools that help them do that better, faster, cheaper. And there's a lot of different trade-offs in doing this. We're building a system that relies on fundamentally new research. We have a few dozen papers and workshop papers at like AI Stats, NeurIPS, ICML. We're trying to actively contribute to the field. We collaborate with a lot of different universities around the world. We pull in a lot of academic research. As soon as something's published, we look at it, determine whether or not we should code it up. If we code it up, we need to A/B test it against our current ensemble, see whether or not it actually made a real empirical improvement, or maybe it was just a great theoretical result for now. There's a lot of different things that we're doing to make sure that we can continuously push this forward. And it's not just the optimization engine itself. It's not just having the best ensemble of different Bayesian and global optimization techniques behind a simple API, but it's about making it accessible. It's about making it a little bit more explainable, having experiments, insights, and dashboards. It's about making sure that it's not cobbling together brittle academic open source, but that it's an enterprise platform that can service our customers around the world, that it just works for up to millions of experiments or tens of thousands of observations or high parallelism or whatever it is that that person actually needs to solve. Because at the end of the day, they don't necessarily care as much about the optimization, they just have this configuration problem that they want solved. And so the team is a diverse mix of people, both on the research side, on the engineering side, the platform and distributed system side, but also on the sales, marketing, and customer success side. You can have the best thing in the world, but if you can't effectively get it in someone else's hands, that's the same as not having it. Going back to what Peter said, research is great, but getting people to actually use it and affect what they're doing is how you actually amplify those results. And so we've made a big effort over the time of thinking of each of the individual departments within SigOpt as multiplicative towards our potential success. Over-investing in one doesn't necessarily optimize the outcome of the company, and not investing in another is the same as not doing any of the other things. So it itself is this global optimization problem with very expensive samples, but trying to solve it every day. And over the last 5 years, we've had the privilege to work with a lot of different people. We're very popular in the algorithmic trading and hedge fund spaces. We help companies with a combined over $500 billion of assets under management tune their different systematic strategies, their different machine learning strategies that affect their trades. Public companies that we can mention are Two Sigma, Tower Research, but many of the other ones that are probably trying to recruit you today. In addition to that, we help a lot of the Fortune 500 and Global 2000. The market capitalization of companies that are currently customers of SigOpt is over a combined $1 trillion. So many extremely large companies in diverse fields like movie streaming services, to global technology consulting firms, to more research-oriented companies like OpenAI that uses us for robotics tuning. But the thing I'm most proud about is some of the stuff that we do when we give away the software for free. So over 100 universities around the world are using our free academic licenses to extend their research in material science, in policy, in healthcare. Really a lot of different fields have this problem, and by creating a simple interface to solve it, now they have access to the same tools that you as applied mathematicians have. In addition to a lot of the work we do with national labs and the US intelligence community and beyond. And that's really the goal of SigOpt, why I started it. The dent I hope to make in the universe is to empower the world's experts to focus on their expertise, maybe amplify it a little, accelerate it a little, but hopefully that rising tide lifts all ships. And if we can make every researcher never have to do trial and error, blind, random search again, I think the world becomes a better place. So, any questions about SigOpt before I rapidly, in the last 10 minutes that I have allocated, talk about some cool applied Bayesian optimization problems? Awesome. Cool. So as I mentioned, there's a couple of different things, areas that we focus on within SigOpt. We've extended some of this into a lot of very unique features, differentiated features from some of the academic open source and things like that we like to collaborate, and that pushes the field forward, but might be a little bit different than some of the real world constraints that we see or requests that we have from our customers. I'm going to briefly run through 3 different things that we do that are extensions of that original open source that I did, that vanilla Bayesian optimization that I talked about in the second section. So the first one, and this was something that we heard almost immediately after starting SigOpt, was, okay, cool, you can tune my system, but I don't have a single thing I care about. I have lots of things that I care about. I'm not trying to minimize the log loss so I can publish a paper. I'm trying to do a bunch of things that compete with each other. I want to have the highest possible click-through rate for my ads, but I also want to show a lot of ads. Don't give me an algorithm that has one ad that always gets clicked. I don't make any money that way. Or in an algorithmic trading sense, I want a high Sharpe ratio or return from my portfolio, but I also want a big portfolio. If I can guarantee a 10x return on $1, that's no good to me. I'd rather have 1.5x return on $1 billion. But I might not know ahead of time how all of these different things compete, how they interact with each other. I want you to give me something where I can set multiple things I care about, set thresholds on things I care about, and solve this more general problem. Because there's not just one thing, there's maybe many things I look at in terms of the business. So what we do is we take that system that I talked about before, inputs and outputs, and we're basically extending it to, okay, now we got a bunch of outputs. Some things we might want to optimize, some things we might want to track, some things we might want to just constrain or put thresholds on, but now solve this problem. So it turns out you need to rephrase the problem a little bit to do this. Again, now we're not trying to find that lat long that gets you the peak of the mountain. Now what we're trying to do is give you a set of solutions that are Pareto efficient. So given two different objectives, in this case maybe F1 versus an F2 in a two-dimensional space, I don't want to just blindly optimize F1, which might represent this point on the Pareto frontier. I also don't want to blindly optimize F2, which might be this point on the Pareto frontier, but I want to understand all possible trade-offs where I can't do any better in one without sacrificing the other. And then at the end, as the expert, you might be able to say, this is the actual balance I care about. This is what I actually want at the end of the day. I want to put it into production. I don't want something that just gets me 99% accuracy for my fraud detection case. I want something that maybe has 98% accuracy, but minimizes also the amount of money I lose to fraud, which is an example from another one of our customers, American Express. So this is a difficult problem in the sense that now we've warped it from just solving one problem to try to simultaneously solve multiple problems. There's a bunch of great research here. Again, this is a somewhat well-studied problem going back to 2006 for this paper. There's a bunch of different ways that you can attack it. And one of the things that we think about a lot at SigOpt is not what's the one right solution, but how do we put together a bunch of different solutions to solve the problem. So one way you could try to solve this is just take those two metrics and do kind of a linear scalarization between the two. Start by optimizing the first metric, and then mostly optimize the first metric and a little bit of the second one, and then just over time slowly shift into only optimizing the second metric. And then ideally, as you can see here, over time, as we modify this lambda parameter, we're kind of sweeping along that Pareto frontier, finding better and better points, and then hopefully we get to a great solution. This works reasonably well, and this is actually what SigOpt does for the first part of a multi-metric experiment. This is a good idea of giving us kind of a loose cut of that Pareto frontier. Turns out it breaks in certain circumstances. If this was concave here, it would only kind of try to sample the edges instead of actually getting that full Pareto frontier. If there's some sort of discontinuity, it starts to break as well. But it can be a good first cut, which then sets us up to be able to attack the problem in a more general way, where instead of just taking the two-dimensional problem and saying, okay, I'm just going to pretend this is a bunch of small one-dimensional problems, we can fundamentally rephrase the problem to say, I want to hit specific areas on that Pareto frontier. Give me my highest expected improvement as long as I'm within some epsilon constraint of it, or within some region or some threshold on one of the metrics. And this has the effect of, instead of just sweeping along that Pareto frontier, we're trying to call our shots. So along this dashed purple line, we want to find a point on the Pareto frontier as close to that as possible, because we have a pretty good idea there's something there. And this helps in this specific case where you might have this large gap in the Pareto frontier that you're not wasting a bunch of time in one region or the other, but you can kind of use this to more uniformly sample it, kind of blow that out a little bit more. And you can further extend this to explicitly disallowing entire regions of the space. A lot of our customers talk about things like, I have constraints on my underlying parameters themselves. Don't give me a neural network with 10 billion layers, because I'm not going to be able to actually train that. But you also might have constraints on the metrics or thresholds that you care about. I want some minimum stability, but after that, go as crazy as you want. I want some minimum return, but after that, give me the best trade-off of 2 other metrics. And this rephrasing of the problem allows us to use not only these epsilon constraints to call the shots, but also try to avoid large regions of the space that the customer might not care about at all. Cool. With the amount of time left, I'm going to start hurrying up a little bit. Lots of cool examples of this. Some joint work that we did with NVIDIA on doing this for different deep learning applications, tuning accuracy versus training time, accuracy versus inference time, etc. Lots of blog posts, code examples online. Again, since you're all academics, you can get free access to SigOpt if you wanted to play with this. Another thing that we heard pretty frequently was, okay, in the purely sequential model-based optimization setting, you might be able to prove some really cool things, but in reality, I might have a big cluster. And if you tell me to only use one node and wait for that to return before giving me the next thing to try, I'm wasting resources. Random search is a pretty naive algorithm, but it's embarrassingly parallel. At least that will use everything. So can we extend Bayesian optimization in some of these methods to fully utilize some of those resources to maybe cut down on wall clock time while potentially increasing CPU time? So we take the same system we had before. Again, it's a black box, so we can just think of this as some worker that can take in inputs and kick out outputs. And our goal is to just extend that across a large amount of workers. So there's a couple of different things we can do here. I'll show you a modification of that sequential model-based optimization method. This was something that actually ended up in my PhD thesis. But again, the nice thing about being an ensemble-based approach is this also opens up the opportunity to try a bunch of different things. Maybe we'll try certain surrogate methods, certain acquisition functions for different kind of parts of our resource allocation problem. But they all learn from each other and expand. So you could basically think about this as taking that 1D acquisition function optimization problem from before, where in this case we're minimizing, sorry for the lack of consistency, where we might say this is the best point to sample, and then map that into, now we can actually select 2 things simultaneously. So sampling the same thing twice might not get me any extra information, but sampling this first minima and this second minima simultaneously actually maximizes this 2D acquisition function space. And you can kind of extend this to arbitrary dimensions where you have the dimensionality of the actual configurations you're tuning and the number of parallel workers you can sample and try to solve that. And you can do that either in that batch setting where you're trying to find the best set of configurations simultaneously, or in a more asynchronous setting where you're just assuming that certain points will come back eventually, and then you're optimizing on specific slices of this space as well. What this does is allows you to, at the cost of compute, which for some of our customers is effectively infinite, have your cake and eat it too. So over one cycle, you can get more exploration and more exploitation. So here's a specific statistical model here, where maybe with expected improvement, we wanted to sample the edge. There's a lot of uncertainty, it doesn't look too bad, sample there. But if we had more samples, we might sample the edge, try to get a little bit more granular information, sample another region, do some more pure exploration over here into the space that's just completely crazy. And we can do all of this at the kind of wall clock cost of 1, get all of that information, update everything we have, and then go back and do it, instead of sampling here, getting some information, and then deciding what to do next. Cool, so we have a bunch of examples here. This was actually some joint work with AWS that we did, showing how you can use this to significantly speed up some, again, deep learning, kind of natural language processing type problems. The final one here is a really relatively new field of research. What if you have super time-consuming expensive functions? So already we made the assumption that it's too time-consuming expensive to brute force, but are we only solving problems in this this Goldilocks zone of well, more than a minute, but less than 5 minutes or something like that? What if it takes a day to train? What if it's one of these larger maybe physical processes in material science where we might need to physically make something and see how well that does before you get an update or a response. So there's this great way that we can take that same problem, and the intuition here is there some way that we can get lower quality, maybe lower fidelity, partial information cheaper, and use that to decide what to do next. Use that to inform the ultimate full cost task that we may eventually care about. So there's a lot of good research here. It's called multitask learning. And the intuition is, in this specific example, we're tuning a support vector machine, and we can break it up into different chunks. Maybe we only train over 2% of the data, 6% of the data, 25% of the data, or 100% of the data. This is the problem we may care about. But what we can do is we can sample this a bunch of times in order to get an idea of, okay, this is the interesting region of the space. Leverage that to decide, okay, now I want to resolve it a little bit more. Looks like this is actually the smaller interesting region. This is where I want to actually do my full samples. And for the same cost of doing one experiment here in the kind of vanilla sequential model-based optimization problem, we can do 50 experiments over here. So use the cheap information to leverage the more expensive ones. Some gotchas here, you need to make sure those functions are actually correlated. The cheap ones lying to you and telling you to sample a different version of the space, you're going to have to unlearn that information. You want to make sure that you're actually normalizing this to optimize what you really care about. Getting the best result on 2% doesn't actually matter because you only care about the 100% problem. But once you do some of these normalizations, it can actually lead you to significantly better results than things like random search, variants of random search like hyperband, or even more traditional sequential model-based optimization. So some cool work here that I recommend checking out. This was one from one of our engineers, Meghna, who recently presented this at MLConf using a more computer vision problem on deep learning. Deep learning is one of these problems that's very time-consuming, expensive. Again, all the code's available online, and there's a deeper blog post to go into it. But with only being a few minutes over, that's the end of the talk. Any questions about some of those applied Bayesian optimization methods?
Perhaps let's thank him first.
Yeah, we can talk in a
We do have a few minutes for questions. I just wanted to make
okay,
sure we all thank the speaker first.
Thank you, thank you. I didn't know how close you guys try to cut it. I guess it was Friday afternoon, so.
I have one big question, like how many metrics can SigOpt handle for this multi-metrics optimization effectively?
Yeah, so it can optimize two competing metrics simultaneously. There's some trade-offs of like the surface area of that Pareto frontier ends up growing quite a bit, which requires a ton of samples if you have more than two. In practice, a lot of our customers can build composite functions of potentially many metrics that are good versus bad or something like that, which gets this kind of interesting Pareto frontier. We can put thresholds on more metrics than that though. So it's like highest Sharpe ratio, highest book size, but the bar has to be less than a certain amount or something like that. Yeah.
So you said like part of the big vision is to get this in the hands of researchers who are maybe doing like trivial testing just to find out. So does your company do anything to make it easy for like a biologist with no coding experience to have access to some of the functionality?
Yeah, so there is a web dashboard where you can manually input results and manually get outputs. Some of the earliest users of SigOpt were like a cosmetics company. They used it to fine-tune the different ingredients of shaving cream. The goal was to maximize the stability so it would actually be a shaving cream and not just a bunch of liquid, but also minimize cost. Or Miller Coors was one of our early big enterprise users that used us to tune some of the various components of the beer brewing process, trying to maximize stability while also minimizing cost. So we have that. The goal, though, is to have the interface literally just be a couple lines of code. So if you can wrap your function, this is one line of Python, Java, R, MATLAB, whatever you have. This is one line. This is one line. If you're doing something like random search, you're basically just changing it from being random to calling SigOpt. In the back there.
So
when you're doing your Pareto front thing, the standard, through the standard graph where you have like f of x and g of x and you're sampling those points, but that's not really you're drawing f of x and g of x, but the problem you are trying to solve is the argmax, so this x. Now I guess my question is, what does that actually look like when you like look at the points in x?
So over here we have F1 and F2. These are the true two-dimensional response surfaces for both of those. And then on the left we have the Pareto frontier.
Is it always so nice? Like
no, this is kind of pathologically nice. So in the real world, even something like this is probably a little bit too nice for what we actually see. SigOpt makes no strong assumptions about continuity, convexity, differentiability, or even that the function is defined over the entire configuration space. So this can get very ugly very quickly. But these represent the x values that lie on that Pareto frontier that you see on the left. So left is output, and then right are the two inputs.
So I guess then my question is if points in there, when they're close, they could possibly be super separated into other space.
Yeah.
Then what if I want the point on the Pareto frontier right in between two of the points? Like I want the argmax right in between 2 points up there. That might be really far apart.
Yeah. So that's effectively what this epsilon constraint based multimetric optimization is doing. Is it's trying to specifically find regions of that Pareto frontier that might be fundamentally different in the actual configuration space. But we get to leverage our statistical models for everything that we've sampled when we're trying to do that. So it's not necessarily trying to just look locally in configuration space to try to push that Pareto frontier out. It's trying to do that larger sequential model-based optimization to find a specific region, which might, based off of that map that we built, point it in a very different direction in the actual configuration space. Which is why here, for example, we have points on the Pareto frontier that are very distinct in this XY space. But there's 3 different regions, it looks like 4 different regions here, but that represent these kind of 2 swaths of a Pareto frontier. Yeah.
Your company is operating in a field that's changing very fast.
Correct.
And when software becomes commercial, there's a premium on reliability, and that tends to slow down development and incorporation of new things. How do you deal with that?
Great question. So that is a constant trade-off that we're having to make. So we do have a full-time research staff that's implementing new papers, trying new things, but there's a relatively rigorous process from taking an idea to taking it all the way into production. So we need to implement it first and do standard software engineering techniques like testing. We need to compare it against all the other methods, or make sure that we actually made an improvement, and that wasn't this kind of spurious or asymptotic result only. Then we put it into our production system. But then the goal is to build that production system in a way that can gracefully fail as well. So if that new thing didn't work, then fall back to the old thing you were doing. If for whatever reason you did something that broke both of those, fall back to something else. And the nice thing about this is, because the standard methods for applying this are relatively simple, we have a reasonable fallback that does no worse than what they were doing before, even at the very, very end when everything's completely broken. So that differs from someone maybe trying to pull down open source and cobble it together themselves, because we can give guarantees or SLAs of 99.99% uptime, or less than a second response and things like that, while still, in the best case, also giving them the best possible things, but gracefully failing and then gracefully extending the research. But it is a constant trade-off, and it is a struggle, and one of the difficult things that we've accidentally boxed ourselves into, but I think we've been able to do a decent job of making those trade-offs. But it is difficult. Yeah.
Are you your own customer? Do you use this stuff to optimize your product?
Great question. Yeah. So not to optimize the underlying optimizer, but I do use SigOpt a lot. We do hackathons every quarter, which is the only time I get to code. So I recently created a SigOpt experiment. This this is extremely meta, but it's, okay, so I wanted to come up with an example that I could show of SigOpt that was both fast and interesting. So I needed to come up with a data set that if I used a standard machine learning model, I could go through an entire SigOpt optimization loop of many observations in less than 2 minutes, so I could show it on a phone call and a demo. But I also needed it to be hard enough that optimizing it didn't just get me like an epsilon improvement, it actually got me like a 5% improvement. So what I did is I was able to parameterize a data set with like 8 different parameters. For each parameterization of that, I could run 10 individual SigOpt experiments to create a distribution of potential times and responses. And then I can take the output of that and create a meta SigOpt experiment that's trying to Pareto optimally maximize the return while minimizing the amount of time, and effectively came up with a solution that was completely non-intuitive to me, but got in the worst case, a 10% return on a gradient boosted classifier method in less than 2 minutes. And now that's what we can use for a lot of our sales demos. Cool. Yes.
So, how light or heavyweight is the compute that SigOpt itself owns and has to use for this? I mean, obviously the algorithmic contributions are the main thing, but what level kind of in-house compute do you have to make this all run?
Great question. So I've given a couple of talks at AWS reInvent that goes into quite a bit more detail, but at the high level, our goal is to employ a bunch of these Bayesian and global optimization techniques in a backend on our side and try to do as much pre-computation as possible so that when we do get that result from the customer, we can quickly reorder things, quickly make decisions, quickly make updates, and give them something to try in less than a second, which is very different than some methods that have to build a big Cholesky decomposition and spend a lot of time computing things. So we do have a relatively robust and scalable infrastructure that's distributed across different data centers around the world. But a lot of that is just very CPU bound and something that's mostly just computing in the back end while we're waiting for something to do. So it's typically less than what our customers are doing, and we have to kind of factor that into our pricing. But, yeah. Yes?
So what are the limits, sort of in dimensions that you can handle for things like type of parameter tuning?
Great question. So in production, customers have used this to tune up to 100 dimensional problems. Up to 100 asynchronous suggestions simultaneously, up to about 10,000 total observations, and then up to millions of independent experiments, but that's kind of trivial for us to scale. Yeah.
In the background, you have some function of x. You're trying to do this argmax. That's your core thing.
Yeah.
If the original function was convex and smooth, you have other things which are way faster.
Oh, yeah.
And if the output was generated by a random number generator, there's nothing you can do this better. So can you just sort of give a sense of how good different methods are, how you characterize the parameter between smooth, convex, and random? So
yeah.
If you did this, if you used your method on a smooth, convex problem, how much worse is it than
Newton's method or something like that? Yeah.
And then where
Yeah. So. The more information you have, the better you can do. And the no free lunch theorem still applies, that this is not going to be everything always, by any stretch of the imagination. How we typically measure ourselves is against whatever method that they're applying today. So if it's a convex optimization, continuous convex optimization problem, and they're applying Newton's method, and they compare us, we're going to do worse in that problem. But when you apply Newton's method to one of these non-convex, non-differentiable functions, that we're going to do quite a bit better. So it is extremely empirical and different problems.
But there's no rules of thumb or a way to describe the landscape, or CMAES they use, that's not differentiable, and that's.
Yeah, so anywhere that you would use CMAES would be, and that's often something that we actually replace for our customers when we go in and do maybe a head-to-head comparison. But at a high level, it's maybe less than thousands of local optima and less than thousands of discontinuities.
That's when you're good.
Yeah, which describes a surprising number of overall.
But a few, but you're also not good when there's only 2 discontinuities and 2 local, then you're also bad.
I mean, if there's 2 local minima, then we'll like 50% do better than a local search.
No, but they can move through this as
Well, yeah, I mean, you're not guaranteed to necessarily, it's a network, only 25% better, but yeah, I guess depending on the space, but yeah, so once it becomes non-convex, or, I mean, even if it is continuous and differentiable, but you have no way of actually analytically calculating that, again, calculating the stencil to do hill climbing is itself incredibly expensive. So even in that method, I would recommend trying techniques like this. But again, if you can make strong assumptions, there are significantly better outcomes out there. We're mostly designed for where you can't make those assumptions. Yeah.
So you mentioned Gaussian processes at many points, but I'm wondering, is there ever a place for heavier tailed statistical models?
Yeah, so Bindle is working on some stuff like that as well. There's also just other, we just need a surrogate representation of the space. So depending on what assumptions we want to make about that response surface, we can slot in other methods. And I know he's been working on some different transforms, and like a t-distribution. You could also effectively use any surrogate methods. You're using that as a way to calculate that expected improvement or that acquisition function. There'll be different trade-offs for ones. You can try to split up the space. You can add multiple ones together. Parson estimators is another one that's popular in the space. But yeah, you start to introduce quite a bit of free parameters once you start to open it up quite a bit. So typically how we attack that is when we see classes of problems that we don't think we're doing well enough on, then we'll invest in research to try to do better in that class. And then if we can discriminate between those classes as the customer sets up the experiment, then we can automatically slot them into a different method.
Yeah, we probably should stop at this point and continue our refreshments next door, but let's thank the speaker once again.